Okay, good morning, everyone. Chapter 4, Logic Circuits. We've covered quite a bit of Chapter 4, and today we're going to cover a whole lot more. Well, kind of redundant to say that, of course. Let's do a quick recap of digital logic circuits. Okay. So far we've studied analog circuits and analog circuit analysis. In this chapter, we're looking at digital circuits and what it exactly means. So analog signals are continuous signals. They can take any shape or form. Digital signals only have two values versus analog that can take infinite number of values, right? So when you plot a analog signal versus a digital signal as a function of time, digital signals have fixed values for certain periods of times. And those values are described as either high or low. High is basically logic 1, and low is logic 0. Okay. In simple mechanical terms, 0 is described as being off, 1 is described as being on. So mechanical light switch has two states. Logic 0 for that would be off. Logic 1 or logic high would be on. Digital signals have some inherent advantages over analog signals. The main advantage is that it has very high signal to noise ratio, because we are transmitting data simply as ones and zeros, meaning a fixed level. And to describe that fixed level, it has a built-in tolerance for any noise signal that may affect our actual input signal or actual output signal. When we create a digital system, we have certain noise margins. Noise margins means there's a certain portion of the voltage that we consider as high, and a certain portion of the voltage we consider as low. So for example, if we say this is from 0 to 5 volts, then high, logic 1, can be described as the top portion of the voltage, which is 3.5 to 5 volts. And logic 0 is described as 0 to 1.5 volts, which is at the bottom, lower end. And then in the middle is undefined region. The undefined region is what happens when you see glitches on your television screen. Either some data bits have dropped out, or the voltage has dropped. For some reason, there's some interference in the circuit, and you see those pixelated dots that appear on your screen. Okay. So digital circuits use binary number system logics, and binary number system basically has either logic 1 or logic 0, 1, 0, 1, 0. Okay, this only has two values, only has two states. There is no middle. There's no values in the middle. So for that, we study the binary number system. The binary number system has a base of 2. We are mostly familiar with the decimal number system, which has a base of 10. Everything else works pretty much the same way. Digital information is transmitted as bits. Each bit is one circuit. Okay, each bit is one circuit. That circuit could be made up of one transistor, two transistors, 4, 5, 6, 7, 8, depending on the kind of circuit or the kind of logic we want to use. The number of transistors would depend on the kind of circuit we want to use. So each bit is one circuit, and collectively 8 bits make up a word, and that word is known as 1 byte. And byte is, of course, what we use in everyday life in computer systems. So binary number system. As an example, let's take a look at the number 1101.11. Now, if you break this down, if it's base 10, we can take the digits to the right, meaning the decimal points, the fractions, and multiply it with the negative exponent, and the numbers to the left, multiply it with the positive exponent. So 0.11 can be described as 1 into 10 raised to minus 1, right? The first decimal point towards the right, 10 raised to minus 1. Second decimal point towards the right, 10 raised to minus 2. And third decimal point would be 10 raised to minus 3. Fourth would be 10 raised to minus 4, so on and so forth. So those are the decimal points. Towards the left, you have a positive exponent, so it's 10 raised to 0, 10 raised to 1. The first digit place, of course, it's always raised to 0, so 10 raised to 0, 10 raised to 1, 10 raised to 2, 3, 4, and so on and so forth. And that gives us 0.01 to the far right, 0.1 right after the decimal point. Here you have 1, 0, 100, and 1000. That's the typical way we create numbers in the decimal system as well as the binary system. However, when we want to convert decimal to binary, if you want to convert decimal to binary, binary uses the base 2. So if you want to convert from decimal to binary, then we have to multiply with the exponent with the base 2. So it is 2 raised to, so here's the decimal point. Maybe I should say binary point. And it becomes, it becomes 1 into 2 raised to minus 1 plus 1 into 2 raised to minus 2. And then if we had 3 digits, it would be 2 raised to minus 3, 2 raised to minus 4, so on and so forth on the right side. It's 2 raised to minus on the left, 2 raised to plus. So on the left, as we move towards the left, it becomes 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on and so forth. So if you take this number, we have 1101.11. So here's 1101.11. Digits to the right are multiplied with the negative exponent. So it's 1 into, starting at the far right, 1 into 2 raised to minus 2. The next number, 1 into 2 raised to minus 1. Does everyone see that? 1 into 2 raised to minus 2, 1 over 2 square, 1/4 gives us 0.25. The next digit again is 1, 1 into 2 raised to minus 1, which is half, 1 over 2, 0.5. Okay. And then on the right, this is the decimal point here. On the right, on the left, 1 into 2 raised to 0, 0 into 2 raised to 1, 2 raised to 2, 2 raised to 3. Let's take a pause, longer pause this time, because this is the first time we are actively thinking about how a number is created after a long time. So let's take a pause, think over that. Let me know if you have questions. Any questions? Do the steps make sense? Right. Now, thankfully, modern calculators, we don't have to actually do this, but as engineers, you should be aware of how this comes about, right? This is the fundamental, fundamental operation of how numbers are created. Calculators, computers can do all of this for us in an instant. But as engineers, you would be designing those systems. You would be designing those calculators, perhaps, be working with those kind of systems. All right. So then we get 8 plus 4 plus 1 plus 0.5 plus 0.25. When you sum it all up, you obtain 13.75, which is the decimal equivalent number of 1101.11. Okay, that's the decimal equivalent number of 1101.11. Okay. All right. I already showed you this last class. Let's go the other way. If you have a decimal number and we wish to convert it to binary, well, base 2, so we divide by 2. So here is an example of 343. Question is, what is the binary number representation of this decimal 343? So if this is decimal, we typically represent, if you're working with different number systems, then we represent the base as a subscript to that number. Base 10, and what is this number, which has a base 2? Okay, because you're going from decimal to binary, we divide by 2. We divide by 2 until the quotient is 0. Okay, so you have 2 lines. You have the quotient and you have the remainder. If you're dividing by 2, the only option is either 0 or 1, right? If you divide any number by 2, the remainder has only 2 options, either 0 or 1. And that's the principle of using this technique. You take 343 and you divide it by 2. That's the number we want to convert to binary. So 343 divided by 2 gives me a quotient of 171 and a remainder of 1, right? 171 times 2 is 342. Odd numbers, you will always have a remainder of 1. Even numbers will always have a remainder of 0. 171 divided by 2 gives me 85, remainder 1. 85 gives me a remainder of 1. 42 gives me a remainder of 0. Again, even numbers will always have a remainder of 0. Odd numbers will always have a remainder of 1. So you keep on going until the end where you divide by 2, your quotient is 1, your remainder is 0. Now, if you divide the last remaining quotient, last digit, you get a fraction, half. It's 0.5. So the quotient is 0, and we say remainder is 1. When the quotient becomes 0, that's when we stop. And then we simply read the number in the reverse order, starting with the last. And that gives us 101010111. And that is the binary equivalent of 343. 343 can be written as 101010. 1 0 and 1 1 1 with a base of 2. Let's take a 10-second pause. Let me know if you have any questions. Any questions? Yes. Yes. Question is, would this be considered a byte? The answer is yes. Any other questions? Yes. So the question being asked is, since this has 9 digits and a byte has 8 digits, would it be like partition? So this is just a random example, but the answer is yes. And there are limitations in systems. So remember a few years ago when they were talking about 32-bit systems in a computer doesn't make sense. We have to like move to 64, otherwise we are limited. The reason is computers, again, binary system, the base is 2. So if you have 32 bits, 32-bit lines, the maximum amount of memory that we can access is 2 raised to 32, which is limited to 4 gigabytes of RAM. So if you wanted to use, so when you do that calculation, it comes out to be 4 into 10 raised to 9. Now, a kilobyte is not exactly 1,000. It is 2 raised to, and so the answer is 1024 bytes. That's why if you use a Windows computer, Windows shows you the actual number of bytes. And so if it's a 500 GB hard drive, it's not quite 500 GB. It'll be less than 500 because of the number of bytes. Anyway, we're getting off track. But I always love to have those kind of discussions. So we converted decimal to binary, but let's talk about what it actually means and how it is, well, a little bit about how it's actually implemented, right? So what does it actually mean? On the left, we have 343. On the right, we have just like 1001, 1111, some number, right? On the left, we have decimal numbers. On the right, we have binary numbers. What does it actually mean? In the simplest of terms, think of the left-hand side as in decimals, as humans, and the numbers on the right as machines. Okay. We are trained, our human brains are trained on the decimal number system, ever since we started learning numbers. We count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we count to 100, we count to 1,000. And that's how our brains are thinking. Machines, even though we say we are living in the world of artificial intelligence, cannot think for themselves. Okay, machines cannot think for themselves. So what we can do with those, what we have to do with those is we have to talk or speak in their language. So on a computer screen, we might type in 343. If you type in 343, there is a digital logic circuit inside the machine, whether it's a calculator, whether it's a computer, whether it's a smartphone, with anything, that converts it into input voltages and currents. Okay. So here we have 9 digits. It could be 10, it could be 15, it could be 16, 32, doesn't matter how many it is, but let's say 9 digits. So it's 9 individual circuits, 9 outputs. And each output can either go high or low, meaning the output of that individual circuit can be either plus 5 volts or it could be 0 volts. So when we type in 343, inside the machine, there are circuits that have transistors, resistors, capacitors, depending on the kind of circuit we have. And the output of each circuit represents 1 bit. The output of each circuit represents 1 bit. So it's a 9-bit, as you pointed out, it's a 9-bit number right here. would be 9 different circuits, and each circuit could have multiple transistors, but one single output. Okay, one single output. And each, as I said, each bit requires a certain number of transistors to represent itself, but that output can only take 2 values, logic high or logic low. So it's either 1 or 0. In terms of voltages and currents, the output of the transistor would be at 5 volts or at 0 volts. And again, that's because humans and machines don't speak the same language. All right, does that make sense? Let's take a pause. Let me know if you have questions. And again, that's a very simplistic explanation, but I found it works very well. Any questions? Okay. To take that example of computer systems further, if you had a 2-bit system, then the maximum amount of memory or maximum amount of circuits you need would be 2 raised to 2, would be 4. A 32-bit computer would have 32 circuits for each bit. It'll be 2 raised to 32. It comes out to be 4 gigabytes. 4 gigabytes. So it can address only a maximum of 4 gigabytes. And that's why they moved to 64-bit systems. I can't remember what that number is, but 64-bit systems can address or access about terabytes of RAM. It's 2 raised to 64. I can't remember exactly what it is. Simple calculation, right? Anyway, so if you're going to decimal to binary, for decimal numbers, fractions, then we multiply by 2. Remember when we went from decimal to binary for whole numbers, we were dividing by 2. For fractions are reciprocals, and so for fractions we are multiplying by 2. So we multiply by 2 and we write on the whole number. So for instance, 0.392 times 2 is 0.784. The 0 is carried over here. The decimal points go here. And then take 0.784, you get 1.568 when you multiply by 2. The 1 goes here. And the remainder, 0.568, goes towards the right. And then you keep going. 0.568 gives you 1.136. That 1 goes here. And then 0.568, the remainder 0.136 goes towards the right. And you can keep going as far as you want to go. It'll never end. Mathematically speaking, it would never end. You could, this is just 3 decimal places. You could take 4, 5, 6, 7, 8, 9, depending on how much precision you require. So you can keep going as far as you want to go. But you would simply read it starting from the top, and you would get 0.011001. So decimal numbers, you multiply. Okay, you multiply. So far, so good. Let's perform a few operations. And the primary operations we look at is addition and subtraction. Okay, addition and subtraction. Now, because we are talking about circuits, circuits cannot actually add or subtract. Okay, if you take two inputs together and you connect it together, automatic, the effect of the two inputs going in together is that it's a summation. Okay, so in that sense, we say that the circuit is performing addition. Okay. So if you have two numbers, you only have 0 and 1, you add 0, 1 and 0, 1. 0 plus 0 gives you sum of 0. 0 plus 1 gives you a sum of 1. 1 plus 1 gives you sum of 0, and 1 plus 1 plus 1 gives you 1. In every instance, there is a carry. For the first one, it's 0. Second one, it's 0. And the third and the fourth is 1, 1. The way we would read this is actually the opposite. So you would have carry bits on the left and the sum on the right. So if it's 0 plus 0, the sum is 0, the carry is also 0. If it's 0 plus 1, the sum is 1, the carry is 0. That means the result of 0 plus 1 is 0, 1. Okay. For 1 plus 1, it becomes 1, 0. 1 plus 1 plus 1, it becomes 1, 1. And let's translate it to actual decimal numbers. So here, 0 plus 0, 0 plus 1, 1 plus 1, sorry, 1 plus 0, and 1 plus 1. 1 plus 1 plus 1. 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 1, 2, 3. Right? Those numbers represent 0, 1, 2, 3. So if you have 0 plus 0, carry is 0, sum is 0. Easy enough. If you have 0 and 1, 0 plus 1, what are we adding? For the first one, now I'm writing in terms of decimal. 0 plus 0 gives me 0. 0 plus 1 is decimal 1. 1 plus 1, 1 plus 1 means I'm adding, in the decimal terms, I'm adding 1 plus 1. The answer should be 2. And so if I get 1 plus 1, decimal answer is 2. And 1 plus 1 plus 1 gives me a answer of 3. Let's take a pause while you look at that. See if it makes sense. Does it make sense? Again, in digital system, meaning it's a circuit, you have 0 volts being added to 0 volts. The answer is 0 volts. The circuit 0 plus 1, meaning one circuit has 0 volts and another has 5 volts. You add it together, the answer is 5 volts. And if you have 2-digit outputs, meaning one is carry and the other one is sum, then the sum is 5 volts, the carry is 0 volts. At our end, that voltage is translated, we convert it into digital logic, and then the circuit inside displays the decimal output. And so we get 0, 1, 2, 3. 5 volts plus 5 volts gives me an answer of 0 volts for the sum and 5 volts for the carry. On the display, let's say if you're talking about a calculator, I would see the number 2. And again, this is a simplistic example, of course, just a 2-bit calculator, 2-bit summation. Okay. And then 1 plus 1 plus 1, you have a carry forward, and then that gives you an answer of 5 volts, and 5 volts translates into 3. Make sense? Hopefully. It takes a long time to grasp these concepts. And again, as I stated, EE students spend an entire academic year learning about these. And so it definitely takes a while. Okay. So binary addition is easier to implement with circuits. Okay, as I said, if you have a summing amplifier, you take 2 inputs, you connect it together, and the result of that operation is that the output voltage is a summation of the input. Okay, so we say that the circuit is performing addition. Okay, but it's not a sentient being to perform addition. Subtraction, however, has no implementation. So the way we implement subtraction is by adding. Okay, we add. And that's where the principle of complements come into the picture. Just the word complement. Some English language, same words might have many meanings. Here, complement means opposite. It complements, supplements, and complements. Complements is, in this case, kind of opposite. Okay. So once complement is easy enough. You have a number, let's say 0, 1, 0, 0, and 1, 1, 0, 0. This is the original number. And then a complement would simply be inverting all the bits or all the digits. Always make that mistake. Ones, I always like to state it as first, the first complement. So ones complement, that has the technical name for that. So ones complement is simply taking the original number and inverting it. Okay, simply taking that number and inverting it. And inverting is very easy to implement in a circuit. You simply take a transistor, apply an input, and the output is inverted. Right? Everybody remember that? So inverting is easy. Summing up is also easy. So the result being addition, or the mathematical operation of addition. Now, there's a purpose to this. As I said, we cannot directly subtract. There's no way to implement subtraction in a circuit. So we use logic. Okay, hence the title, digital logic and logic circuits. We take ones complement by inverting every single bit, every single digit, meaning if 5 volts goes to 0 volts, 0 volts goes to 5 volts. That's easy enough to implement in a circuit. Then there's something known as 2's complement. 2's complement is simply taking the ones complement and add 2's complement involves adding 1 to the least significant bit of the ones complement. Okay. So 2's complement is equal to 1's complement plus 1. That's it. That's all it is. So the ones complement or the original number, I'm going to write it here. You got 0, 1, 0, 0 and 1, 1, 0, 0. That's the original number. Ones complement gives you 1, 0, 1, 1, 0, 0, 1, 1. Oh, by the way, binary numbers are read exactly the way we read decimal numbers. We start with the most significant digit or the most significant bit, and we move towards the left. Okay. It's 343. We read 343. Actually, that's not a good example. 341. 341, we read it as 341. So binary numbers, we use the same principle. We start at the most significant bit, meaning on the far left and move towards the right. My left and my right. So we start on the left and move towards the right. So 1011, 0011. That's how we read binary numbers. Exactly the way we read decimal numbers. So that's one's complement. You add +1 to that number, and you get 0, carry 1. 1 plus 1 again gives me 0, and carry 1 gives me 1. And then from that point on is just 0, 1, 1, 0, 1. The 2's complement is simply adding 1, and that gives me 1, 0, 1, 1, 0, 1, 0, 0. 0, 1, 0, 0. Zero, 1, 0, 0. Let's take a pause while you think over all of that. Let me know if you have any questions. We'll take a short break once I'm done with this slide. Any questions? No questions? Okay. All right. Here shows you another way, another method of 2's complement or writing 2's complement. You simply take the number, the original number, right? 0, 1, 0, 0, 1, 1, 0, 0, and you start at the least significant bit, meaning on the rightmost side, and you write down the numbers. So 0 becomes 0, exactly as they are, until you reach the first one. Once we reach the first one, you stop at the first one, and then invert the rest of the digits. Invert the rest of the digits. So 1, 0, 0, 0, 0, 1, we write it as 0, 0, 1. Now we hit 1 at the third bit or the third digit. The rest of the digits are flipped. Yes. Yes. Good question. Yeah. So I think it got lost in translation. the question being asked is, essentially, what is the purpose of doing this? The purpose of doing this is so we can perform subtraction. That's the gist of the question, right? Yeah. So I think it got lost in translation. Yes, the purpose of doing this is so we can implement subtraction with electric circuits. Okay, subtraction with electric circuits. So we have the 2's complement. There are 2 ways to finding it manually. And once we have the 2's complement, we simply add that to the number, and you get the answer is a subtracted output. So here, let me summarize it right here. Let's say we wish to subtract 2 numbers, A minus B. We would write A as it is. We would take the 2's complement of B, and let's call it B minus, just for this example, okay? Just for this example. Then the answer for A minus B is simply going to A plus B minus. Okay, is because we can easily implement addition using electric circuits. There's no direct way to implement subtraction. Okay. So the purpose of finding 1's complement and 2's complement is so we can implement mathematical subtraction in electric circuits or with electric circuits. Make sense? And we'll look at an example. So let's say we are trying to subtract 2 numbers, and let's first look at the decimal. So 29 minus 27. What is the answer? 29 minus 27. 4. Right? So we, as human beings, we learn about this in elementary school, right? So then our brains are automatically tuned. We don't think how it actually works or why it works. We just know once we learn it, right? In binary number systems, let's translate this. 29 decimal number is equal to binary 0001 and 1101. 27 is given by 0001 and 1011. It requires 8 digits. All right, so we are subtracting 27 from 29. So we leave 29 alone. We leave 29 alone. We leave it as it is. We don't modify that. We don't do anything to it. The number to be subtracted is the one we will modify. Again, we are performing 29 minus 27. So we leave 29 alone. We don't do anything to it. But the number that is to be subtracted, which is 27, we will convert that. We will modify that number. We'll perform the mathematical operation, sorry, the logical operation on 27. So the 1's complement of 27 is 11100100. Right? 11100100. And then in this case, the reason we chose this example, of course, is the 2's complement is rather easy. 2's complement, simply add 1 to the least significant bit. And so it's +1. And that gives me an answer of 11100101. Right? 0101. Now, all we need to do to perform a subtraction is to take the 2's complement of 27 and add it to 29. So 29 minus 27 is going to be the 2's complement of 27, 1110010101, and you add it to 00011101. This is 29. And once you add these two numbers together, let's see what you get. Starting with the least significant bit to the far right, 1 plus 1 gives me 0 and 1. Answer is 10. So 0 here, carry forward 1. 1 plus 0 plus 0, answer is 1. 1 plus 1 gives me again 0, carry 1. 1 plus 0 plus 1 gives me again 0 and 1. Again 0 and 1, 0 and 1, 0 and 1, 0 and 1. Here we can see the resulting answer is 9 bits. And the resulting answer is 9 bits. Then we throw out that extra digit. And our answer is this, which is 2. Right? Binary system, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1, 0, 1, 2. All right, let's take a pause. Actually, let's take a break itself. Think over this. Let me know if you have any questions. If you have no questions, feel free to take a break. Any questions at all? Again, if you have no questions, then we'll take a break. We'll meet back at 11:05.